I think it's a good crowd, and yeah, let's maybe start. It's my pleasure to have Marcelo Campos talking to us about sphere packing results. So he's, I guess, a rising superstar in combinatorics. Well, a couple of years ago, you finished your PhD with Rob Morris, and then been to Oxford and Cambridge, working with all the great people and proving really impressive results, sphere packing, Ramsey numbers, and singularity of random matrices, and so on. So, yeah, it will be great to hear your talk. So, please.
Thank you very much, Andre. Thank you for inviting me. Thank you all for coming. And okay, so today I'm talking about this result about sphere packing. So it's new lower bounds for sphere packing in high dimensions. And this is all joint work with Matthew Jensen, Marcus Michelin, and Julian Sastabudet. Okay, so I'll start by defining what a sphere packing is for me. So I'm defining it just using the centers of the spheres. So we take a set of points in RD and we say it's a sphere packing. If for all pairs of different points, they have at least distance to RD. And here, I'm always going to be normalizing by this radius, RD, which is the volume of the unit ball. Like is the radius of the ball with volume 1. Okay, so here, for instance, these 2 points, their balls are disjoint because they have distance at least to RD. So like if you place balls of radius RD with centers in this set P, then you have a sphere packing. By the way, please interrupt me to ask questions at any point if like I'm saying something that is not clear or you just have a question. It's like very helpful. And then we define this quantity here, theta d, which will be the main quantity we're interested in today, to be the supremum over all sphere packings of this limit here of the number of points in the sphere packing in this large box of size L by L, and divided by the volume of the box. So basically, since I'm normalizing, so the balls have volume 1, this is like the volume of that the balls take, of the sphere packing take inside this box, basically. And you can show that you can switch this supremum and this limit by some standard arguments. So we are actually going to just be thinking about a very large box, fixed, and then like trying to look at the largest sphere packing inside this box. Okay. And okay, so this quantity is interesting even for small numbers. Like so, even in small dimensions, it is interesting to determine what the volume of this theta d is. So for theta of 1, it's trivial because balls are just intervals, so it's just you can perfectly pack. But theta of 2 is already interesting. So it was solved in the beginning of the 20th century by 2. And he showed that the density for 2 dimensions is given by this hexagonal lattice here, and it's about 90% of the space you can cover. So you really cover a lot of the space. But then it was only in the turn of the 20th century that they calculated exactly what theta of 3 is. So in 3 dimensions, which was a famous conjecture from the 17th century by Kepler, that this cannonball type arrangement is the best packing. So it's also a lattice, and it takes up 74% of the space. And I should say, like, in all these problems, like the construction is just this construction I'm showing you, so it's very easy to see like the lower bound, so because it's just given by this construction. But the upper bound was the hardest part. So also in this two other dimensions where it's solved, in dimension 8 by Vyazovska in 2016, she showed the E8 lattice is optimal, which is a very, very symmetric lattice that exists in 8 dimensions. And in 24, there's also this cousin of the E8 lattice, which is also very symmetric, the Leach lattice, which is also shown by Komar, Miller, Radchenko, and Vyazovska based on her method. And it's already much smaller density, 0.002. And you can see, like, okay, the density is dropping as the dimension increases. So you can ask, okay, how fast is it dropping? Like, what is the, can you get like any asymptotics on this dimension? And as we see in small dimensions, the constructions are kind of given by these lattices. And the hard part is showing that this is optimal, like showing the upper bound. But in high dimensions, even the construction is not clear. Like, what is the best lattice to take, or what is the best construction to take in general? And for upper bounds, there's this very interesting paper by Kapaczynski-Levenstein from 78 that shows that this decays exponentially with exponent 2 to the minus 0.99 times d. Plus little od. So all the results I'm saying here are going to be asymptotic. So sometimes I might not put the 1 plus 0.01, but assume all the results have a 1 plus 0.01 in case I don't put it. And for lower bounds, there's a general lower bound of 2 to the minus d that is easy to show because it just comes from taking any packing, any sphere packing in the box that is maximal, so that you can't fit any more balls in that. And I'm going to show this is if you take any packing like this, it gives 2 to minus d. And so this will be this 2 to minus d will be our baseline because there hasn't been any improvement in the exponent for this 2 to minus d. And it's a big problem to find out what is the correct rate of decay. And yeah. I'll talk more about it in a second. So let's show this 2 to minus d bound. So you take a maximal sphere packing in the box, and it means that since you can't fit any more points in the sphere packing, it means for all the points in the box, there is some point in the packing that is close to the point, right? So by our definition, if this point was at distance at least 2RD from all the points in the packing, we could include it. So it has to be a distance at most 2RD from some point in the packing. But then this means that the box is fully covered by these balls of radius 2RD center at our sphere packing. But then, like, just by the union bound, just by looking at the volume of this versus the volume of this, is the volume of this guy is at most the volume of this guy, which is the sum of the volumes of the balls, which I'm normalizing so the ball of radius 2RD has volume 2 to the d, and then it's times the size of packing. So you just rearrange, and you see that the packing over 2L to the d has size 2 minus d. So this shows the lower bound by the definition of theta d. Okay. So the question is, okay, this is 2 to minus d will be our baseline. So the question is, can we do better? And there have been many improvements across the years, and I'm listing them here. So all these improvements, they involve a basic technique that was first developed by Minkowski, like the first important observation was by him, that if you take a random lattice, you can basically attain this 2 to minus d bound, but you can also do a little bit better by using the symmetries of the lattice. So Minkowski here, he does better by a factor of 2 by basically using this following symmetry in the lattice, that if a point x is in the lattice, a point minus x is also in the lattice. So this like kind of doubles the number of points in their sphere packing by using the symmetry. And then the idea is to, if you put more and more symmetries in your lattice, you can like get better bounds. So Rogers used a much more sophisticated technique for analyzing random lattices to get this bound here, 2 over e times d, 2 to the minus d. And then all these improvements here are just on the constant in front of Roger's result. So basically he got this d times 2 minus d, and then like the constant here is the improvement in all these cases. So by Davenport Rogers, and then by Ball, then Vance when d is divisible by 4. And finally, Venkatesh has this amazing result here that he showed like 65,963 as the constant. And also, he gets a very interesting result, which he gets the first asymptotic improvement, so much bigger than one improvement, but not for all d, only for a sequence of d's. So basically, when d is the product of the first k primes, you can find like a special lattice with some number theoretic properties that has this density here. And so so like it's something to do with
Marcel, just a small question. So Minkowski, you said Minkowski used the random lattice, you said,
yes,
right? And Rogers as well.
Yeah, so they are all
but not Venkatesh or Venkatesh also.
They are all using random lattices, but from different groups of symmetry of the lattice. So Venkatesh basically uses a very restrictive group of symmetries in the lattice. Like his lattice is random, but like with like a lot of symmetries. So that's why he gets this better result.
Okay.
And so our result is this. We show the first asymptotic improvement for all dimensions over Roger's result. So we show this log d over 2 thing in front of d 2 minus d. And our result doesn't use a lattice. Instead, it uses a very random-like packing. And it's interesting because it's almost attains this conjecture by Parisian Zamponi. I'll put here conjecture. So it's like a prediction by them. They're physicists, and they say that the densest amorphous sphere packing should have density log d times 2 minus d. And here the meaning of amorphous is I think it's not like mathematically defined, but probably like something like our sphere packing should be amorphous. So like something like that has like no discernible structure. And basically the idea is that if there isn't like a special type of structure in high dimensions, this should be the densest packing. So this should be the best thing possible up to this factor of 2. And this factor of 2 is very related to a problem in combinatorics, a famous problem even in Ramsey theory that we can discuss in a bit. And so it's a very interesting problem to try to attain the Parisian Zamponi prediction. So to obtain log d times 2 minus d.
But will you give later this motivation for the conjecture?
Yes.
Why do they give this log d times d? Yeah. Okay.
So the way they get to this number, I don't understand it, because it's a very interesting technique in physics called the replica method, which is kind of like, as a mathematician, it's very impressive that it works, because it's like they do like manipulations that we wouldn't say are valid, but for some reason they can get like very good predictions. And so their technique to get this prediction has nothing to do with ours. So, but somehow we see the same type of prediction in our model.
Interesting.
Okay, so now I'm gonna start talking about. So yeah, the objective today is like I wanna basically talk about the proof of this theorem. And I probably can go quite into depth in this, because the proof is fairly short. So, and the proof uses basically a translation of the problem into a graph theory problem. So I'll convince you that now that basically this sphere packing problem is secretly a graph problem that is hiding there. And the reason is that if you take any subset X of your box, let's say a finite subset, then you can define the following graph, Gx. We define this graph as the pairs xy such that so they are both in x, and the distance between them is at most 2RD. Okay, so if you define this graph, now it's interesting because any independent set in this graph is going to be a sphere packing, just by definition, because a sphere packing is just a set of points such that every pair is a distance at least 2RD. So you just can't have any edges of this graph. And so basically, so if P containing X is independent in Gx, implies is a sphere packing. So basically, notice that our quantity D then will be bigger than the independence number of this graph, Gx, over our quantity here, 2L to the D, right? As long as remember, X is contained in the box. So if we can find a very good lower bound for the independence number we can find, okay, so there are two steps. First, you need to find your finite set X. And second, you need to find a very good lower bound for the independence number of your graph Gx. And so if we can find this set X and a good lower bound for the independence number of our graph, then we'll be happy basically. So the idea here is that we're basically going to choose. Not going to be too clever about how we choose X. So X is just going to be a post-some-point process. So it's just going to be something that basically discretizes the box decently well. So it has all the properties of the infinite box, but then it's finite, so we can kind of deal with it. And then the main point is going to be how we show the lower bound on the alpha of Gx. So we're going to need certain properties about the graph to show that. Okay. And okay, one nice thing is for instance, there's this theorem, which is very classical in combinatorics, which is this theorem by the Turan's theorem, which most people should be familiar with, which just says that if you have a graph with G and delta of G is the most delta, then alpha of G is the least n over delta plus 1. Okay. And notice that this is optimal in general because you can take a bunch of cliques of size delta plus 1. And okay, of course, this graph has sorry, I should put VG. Has independence number exactly V of G over delta plus 1. But we could try to apply this theorem first to our graph and see how it does. So now we have to choose X. And as I said, we could just choose X to be like a post-some-point process. And in the box.
I think just in case, I think it'll be good to give a definition because not everybody may know what exactly they mean by that.
Right. Okay. So the way I think about it is that you just take epsilon. So you just take the lattice ZD and you intersect with some epsilon and you intersect with the box, right? And now So let's call this Q. And now, for each X in Q, include in X with probability. So it has to be the correct probability. I think it's like epsilon. Let me think. It's just basically I just want to include each point in this lattice here independently with the correct probability, so that the expected number of points in each ball of volume 1 will be approximately the will be approximately lambda. So the important point of the post-point process is just that the expected number of points in each set of volume of a given volume will be just lambda times its volume. So let's just say, so roughly the number of points in a ball of volume 1 here will be like 1 over epsilon to the d. So I guess we want to include the points with probability lambda times epsilon to the d. Okay. Independently. And the cool thing about this process is the following. If you just look at the intersection of the, so you just look at X intersection some ball, right? And here you're going to let epsilon tend to 0. So if you just look at the intersection of X with some ball, the distribution of this will be a Poisson with rate lambda. So the size of this one. This is the important point about this process. And so, in particular,
ball with radius RD, so that the volume is 1, right? Okay.
Yeah, exactly. Normally, you need to rescale by the volume. Yeah, sorry. Yeah. Okay, and so the point is that the number of, if we take lambda to be large, the number of points in each ball would be very concentrated just by the concentration of the Poisson in the variable. So we should expect it to be very concentrated about its mean, which is going to be lambda, basically. So we expect to see in each ball, basically lambda points. And, okay, so let me put another slide here. So basically the point here is that the size of X will just be roughly lambda times the volume of the box. Volume of the box. So I'll actually say X, the size of X is going to just be then a Poisson with this rate, volume, which is just a Poisson with rate lambda times 2L D. So we expect the size of X to be roughly lambda times 2L to the D. It's pretty concentrated around this number. At the same time, we can ask here in this, for our graph GX, what is going to be its maximum degree, right? And okay, let's just compute what it's going to be its average degree, actually. So an average degree here is just you just take some point in X, you look at a ball of radius 2RD, and you just want to know the number of points of X around it, right? So this is just going to be the degree of a point. We'll call the point U. X. is this. And this is just going to be a Poisson with rate lambda times 2 to the d. So we should expect for almost all the points that its degree will roughly be lambda times 2 to d. And then what you can do is like, okay, if there is you have this concentration inequality. So for almost all the points, you have degree very close to this. If you don't have degree very close to this, you can just delete the point, and you're deleting very few points from X. So this is all going to be fine. And so it means that after this deletion process, we expect the max degree of our graph to be basically to be smaller than lambda times 2 to d. Okay. So now we can apply Turan's theorem to say something. So let me copy this. Sorry. Okay, so now we have alpha of gx is going to be bigger than the size of x, which is lambda times 2l d, over lambda times 2d. So plus 1. So this is basically like, so the lambdas cancel, and you basically get 2l to the d over 2 to the d. So, and this is very similar to the first bound we proved, right? So Turan is kind of in sphere packing land, is kind of the equivalent to the maximal packing type argument. As you can see, because, okay, we know that theta d, just to remind you, is going to be at least alpha of gx over 2l d. So this is showing a bound of like 2 to minus d. Okay, so if we can do better than Turan, we can hope to prove a better bound here. And the point is, like, I said to you, Turan is optimal, but it's only optimal for that funny graph, which is like a union of cliques. But in principle, there's no reason to think that our sphere packing graph should be like a union of cliques. It could be, it should have some different type of structure. And maybe we can exploit that structure to prove a better bound. Okay. And there is like another type of graph that also has small independence number, which is the random regular graph. So if G is a delta random regular graph, then we have the bound that alpha of G will roughly be log delta over delta times V of G. And you can ask if this bound is optimal. And, well, there's this famous theorem by Aitai Komlash-Zamardi, which was improved by Shearer in the 80s, which shows that alpha of G is at least, sorry, there's a 2 here, 2 log delta. Log delta over delta without the 2, so they don't quite attain the bound from the random graph, if G is triangle free. And okay, so you can ask why they put this triangle free assumption. So basically, they need some type of assumption to get rid of the union of cliques example that shows Turan as optimal. And basically, they need something to say that the local density can't be too large. So one possible condition is being triangle free. So they also have like similar results when the graph is free of k4s, for instance, but they can't quite get the same bound. They lose like a log here, and it's a big problem to actually show the same type of result with k4 free instead of triangle free. So show the same type of bound here. Okay, there is also another problem here.
So, by the way, probably maybe, or you'll say about Ramsey here that this is related to Ramsey, right?
Yes, exactly. So this result is basically the way to you can apply this result to show that R3K. So you have you want to know the Ramsey number of the triangle with red versus K clique with blue. It's at most K squared over log K by applying this result here. So this is the way to show this. And well, it's a big problem to actually show this improvement by a factor of 2 here on alpha of G, because you immediately get an improvement by a factor of 2 in this R3K. And this factor of 2 here that is missing in this theorem, I'll show you in a bit, that is the same factor of 2 that is missing between our theorem and the Parisian-Zamponi prediction, the physics prediction. So it's the same factor of 2 that is missing here.
Wow, that's interesting.
And yeah, and that so we can ask what happens if we now just try to apply this theorem to our sphere packing problem, and we can see what happens. So there is this paper that does this, which is by Krivilevich, Litzin, and Vardy. It's from I think it's from 2004. Which is I think it's like one of the first constructions for sphere packings, that good constructions that don't use a lattice. Like they have a lattice, like a construction that is not a lattice. And well, then they use essentially this term here. And let's see what happens. So they are going to take X. We take it to be a Poisson point process. Again. So just to mind you, the size of X will basically be lambda times 2L. And again, we'll have like delta of Gx. Will again be like lambda times 2 to the d. Okay, and so if you plug this term here in now, we get that alpha of Gx will basically be at least so it's log delta over delta times v of g. So this will be log of lambda times 2 to d over lambda times 2 to d times the lambda to d, which will be like so it shows that alpha of Gx over 2L to D. So the lambdas cancel again, and we get this lower bound of log of lambda times 2 to the D over 2 to the D. So you might say, okay, now of course you just take lambda to be as large as possible and you win a lot. But we have to be careful here, because we can only apply anti-common similarity. So here's AKS. If our graph is triangle free. So we have to choose our x carefully, so the parameter lambda in our x carefully, so that the graph is still triangle free. And then we're going to win while whatever lambda, log of whatever lambda we can choose here, right? And so the best lambda, I'll tell you now, the best lambda we can choose is going to be like 2 to the minus d plus some constant times d for the graph to be triangle free. And then what we're going to get is like basically log of 2 to the constant times d. So this will be basically some constant times d over 2 to the d. So it gives basically the same thing as the Rogers type bound. So like constant times d over 2 to the d. And okay, what is the reason why this is the best lambda? It's basically like how do we compute the so basically we are gonna have triangles in our graph, but we want to have few enough triangles that we can like delete one vertex from each triangle and delete all the triangles this way. So we need to count the expected number of triangles in the graph, and to do that, let's see. So we take like 2 points, and when do they form a triangle? First, the 2 points need to be connected. So the distance here is at most 2rd. And now they have, each one has a ball around it of radius 2rd. And then you must have a third point here in the intersection of the 2 balls. So, but the point here is the following. What is the volume of a intersection of 2 balls? Well, it kind of depends on the distance you want to put between the points, right? And the point is that we need this volume to be so basically the expected number of, so I'll call this point x, this point y, and we'll care about the expected number of triangles, including x and y. And okay, and so this is going to depend, this is going to basically be the number of points in the intersection of these 2 balls of radius 2rd, right? So this says radius 2rd, let's say radius 2rd. And so this expectation is going to be lambda times the volume of ball y of okay, and so basically we need this this quantity here. We need to choose lambda so that this quantity here is very small, right? Like it's much smaller than 1, say, so that the expected number of triangles on top of every pair of vertices is very small. And you can do that if you do the calculations. You can do that as long as lambda is some exponentially small things, like basically 2 to minus d plus some constant here surely works. You can try to optimize what this constant is, but
is it enough to make it smaller than 1, or you need it to be like smaller than 1 over the degree or something like that?
Yeah, I think, sorry, it's smaller than 1 over the degree. Yes. Yeah, you need to like 2 to minus d basically. Yes. And the point is that
times 2 to the minus d, or lambda should lambda 2 to the minus d lambda, no?
Lambda, okay. Yes. Let me think. Yes.
This is how you would win, I guess.
Yes. Thank you. 2 to the minus d times 1 over, lambda to minus 1. Yes. Thank you. Yes, you're correct. But then, the point is that, with this choice of lambda, it's gonna hold, right? Because this thing here will be just basically 2 to minus constant d And this side here, we have a 2 minus d plus this constant. And the intersection between the balls, well, we first have to get rid of points that are too close together, but there are going to be very few of those. And then, like, if the points are far away enough, the intersection of two balls will also be pretty small. So this is the reason why it works, basically. But yeah, I don't want to get like too much into the details of all the calculations because we're going to do something simpler in a minute. Okay, but okay, I just want to say that these triangles are unavoidable in this graph. Like if you take lambda to be higher, there's like no way to get rid of the triangles. You just have too many triangles, and this method really is doomed. You can't just get rid of the triangles here and apply Ita already.
You can also maybe say that a radius of the sphere circumscribed around the triangle. In the worst case, is something like 1 over square root 3, or I don't know. I mean, is like smaller than this radius 1 exponential. Like the radius is constant times smaller than the radius of a ball around the point, and then you can just say that we will basically don't have any maybe balls like that containing 3 points across our point set or something like that.
Yes. Thank you. This is also this is a very good observation as well. Yes. I think this is
At least as an intuitive explanation, if you expect lambda to see like lambda something like 2 to the d over lambda points inside the ball of radius 1, and then you look at ball of radius 1 over square root 3, then if lambda is chosen correctly, then you expect to see none basically, or very few.
Yeah, this is a pretty good observation. Yeah, thank you. Yeah, I never thought about this way, but yes, it's a easier way to see, I think. Okay. So, so then how do we deal with this problem? Then so we want to use like kind of the same strategy, like proving like some lower bound on this. But we just want to take lambda to be higher, like be able to apply something like Ita similarity, but with lambda to be much bigger, and still be able to apply it. And so the point will be that I said that you need the triangle freeness to have like some local sparseness condition, so that we don't see that example where it's a union of cleats. But that's not the only condition you put in the graph. And the idea is basically to find the correct condition that you can put in the graph so that it holds for the sphere packing graph, but it also is something that you can prove the same type of bound for. And the condition we put, it's very simple. It has to do with the codegrees of the graph. So we define dg of uv in a graph would just be the size of the intersection of the neighborhoods of u and of v. And we define this delta 2 of a graph G to just be the maximum over u different from v of dg uv. So this is just the maximum codegree. You have two guys. And we are looking at the size of the intersections, this thing. And the thing we prove is this new version of Ita similarity, which instead of putting the condition of being triangle free, we put this condition on the codegrees. So we should say that if delta of G equals delta, and delta 2 of G is the most delta over 2 log delta to the 7, then alpha is the least. There is a 1 plus 0 1, but no, I'm right. So this is as delta tending to infinity. And that this is the theorem. So now we can just like plug this theorem into our graph problem, and we're gonna be done. So now we're gonna be able to take lambda to be much higher, and still satisfy this condition here instead of the triangle freeness condition. Okay.
So it's not necessarily weaker, right? The condition. So you also impose a condition on points that are not connected by an edge.
Yes. Yes, you are correct. Yeah, it is. I'm not like sure if you need this condition for points that are not connected. It turns out that like it doesn't matter for us, but it might be interesting to like show something that is like strictly stronger than the to show it for also for points that are connected. So that would be like to have this condition, but like a weaker form of like a weaker form of this condition where you just need it for points that are connected. But it turns out that we don't need it for sphere packing.
Okay.
Okay. So that then we have like this. We have a pair. Now we're gonna take lambda to be like d over say log d squared to the d over 2, or maybe I'll put it to 4 here for safety. Okay. So what is the point of taking, so x will be again Poisson lambda. What is the point of taking this sphere packing to be this dense? Is that first, notice that if you have a ball around a point of radius log d, and you take the intersection of x, well, what is going to be the size of, what is going to be the expected intersection? Well, so the fact is that RD is basically going to be some constant times root D. So log D is basically going to be root D smaller than the normal radius of the ball of volume 1. So this ball here has volume like log D over root D and some constant to the D. And then this is finding again. So we get this number times lambda. And we'll be clear in a second why I'm looking at above this radius. But basically I want to say that every pair of points will have distance at least log D in our set X, almost all the pairs of points. And the point is that now this thing is at most. So we substitute lambda in, and you'll get this is at most like 1 over log D to the D. Okay, and so this is cool because it means that we can basically delete any point that has another point that. So basically, we delete any point x that has another point very close to it. So that has so delete x if there exists y with x minus y smaller than log d. And this way, we're deleting a very small proportion of the points. We're only deleting this proportion by Markov. So this is the expectation. So now we assume that all pairs of points have distance at least log d. But now, what is dg of x and y? Like, what is this quantity here going to be? Like the intersection of the neighborhoods? Well, this is just going to be the size of the neighborhood of x intersection the neighborhood of y, which is just the size of the ball around x of radius 2rd, intersection the ball of radius y of radius 2rd, intersection with our points at x, right? But now the expectation of this is so the expectation of this is going to be around its volume, right? So we need to compute the volume of this thing. So this thing is basically going to be like lambda times the volume of the intersection. Okay, let me copy this to the next. And now we just need an upper bound for this quantity, right? But the point is that we just use a very silly upper bound, which is that if you have here x and here y. Oh, sorry. And they have some distance between them. You can take the point in the middle between them. So x plus y over 2. And you take the ball center around this point with this radius here. And the intersection between the balls is contained in this ball. And if you just do some calculation, you see that the volume of this intersection should be at most exponential of minus the distance between x and y squared, say over 8, times the initial volume 2 to the d. And then we have the lambda. So basically, like when the points are very close, then you expect the intersection of the balls to basically have total volume to the d. So it's basically the same volume as one of the balls. But as they pull far apart, this volume decays exponentially. And now the interesting thing is that the distance between any 2 points x and y is at least log d, right? So we know that x minus y, the distance, would be at least log d. So this thing here is at most exponential of minus log d squared over 8 times lambda times 2 to the d. And this lambda times 2 to the d is just is just delta of g, if you remember. So we just showed a bound of the type something small times delta of g. So we just need this something small to be good enough to plug into our theorem, and we'll be happy. So are there any questions about this, by the way?
Yeah, that's fine. So your the missing 2 in your case is this because you take it to the power d half to right? So just coming from the root d behavior of RD or something like that, or where does this factor of 2 coming from is compared to this physicist's conjecture?
So the factor of 2 that is missing is basically the same factor. So is that we should be able to, in the graph theory problem, to put a factor of 2 here.
It's again, okay.
So it's the same, yeah, it's exactly the same as in the factor of 2 is not in the geometry, is actually in the graph theory, in the graph theory.
So you cannot really hope to get anything more from the delta side, like that's not like, or from the lambda side. From the lambda side, I mean.
I think no, because if you take it to be denser, basically, like you notice that when your distance between your points x and y is much smaller. It's like much smaller than a constant, so it's much smaller than 1, say. Then their balls, the intersection between their balls, turn out to be very, very big. So they're basically representing the same point, right? Like they aren't different enough. So the correct factorization for your space is at the scale.
Yeah, you're right.
I have another question. You tried to ban the triangles. Is it a good idea to ban another small cycles? For example, a cycle of 4 points or a cycle of 5 points?
I think you should still run into problems with any small graph, because as your graph gets denser, you actually see pretty large cliques in this graph. So like this graph has like if you look at this graph, like all the like any finite configuration, right? It will happen a lot. So you can't get rid of. So you need to be able to have some forbid like configurations that are growing. So you have like to have like some pretty good bounds on this type of problem with some forbidden like configuration that is getting bigger. So I don't know if that could work, but maybe that could. But yeah, we don't know how to do that, because even for like small things, like it's kind of hard to it's kind of hard to deal with already. Like K4. But yeah, I don't know about cycles. Okay. And okay, so just to finish this, right? So the point is that this we just need to show that this exponential of minus log d squared over 8, for instance, this is much smaller than 1 over log delta to the 7. But what is log delta? So delta will basically be d to the d over 2. So this is basically like 1 over d times log d to the 7 here. And so this guy is obviously much smaller. So we have like loads of room here. Okay, and by the way, it's one interesting problem here is to try to get, like, we have this dependence log delta to 7. I think if you like just do the calculations a bit more carefully in the proof, get cubed here. But this term should hold up to like log delta without any powers, I think. So it would be interesting to try to get it there, because yeah, our term like this, the way we do it, it doesn't quite get there. And okay, so how much time do I have? So I have like half an hour. So yeah, maybe I can try to show a bit of the proof of this theorem.
Yeah, definitely. So now we're basically done with the geometry part, right? Completely.
Yeah, exactly. Now it's just a graph theory problem. So we have just a graph with these two conditions, and we want to find a large dependent set. Okay. Okay, so what is the idea here? We use a technique that is kind of old. It goes back to the 80s. So we use the Rodel nibble with with a little bit more like a bit more, not that modern tools, but like, so just like a bit more careful, because basically the idea is that we're gonna choose our independent set randomly in stages, in rounds. So we're gonna start with our graph here at G, and I'll call G0 to just be G. And we're gonna choose a random subset. I'll call A0 here. And this random subset will basically be almost independent, very few edges inside, like almost all the vertices aren't in any edges. So it's almost an independent set, which is already nice. And then we just delete its neighborhood. So just delete, and then we just zoom into this portion of the graph, which I'll call G1. And we're just gonna keep doing this. So the way we choose A0 is very simple. So I so delta 0 just be delta of G, and A0 will just be, so just choose some small parameter gamma, random subset of V of G. And then, so this just means I'm including every vertex independently with probability gamma over delta 0. And then I'll define, so in general, I'll define gi plus 1 to be gi, and then you just remove a0, ai, and you remove its neighborhood as well. Okay, so this has the nice property that, okay, now we take this other guy here, a1, and since we already removed the neighborhood of a0, we know that there isn't any edges between them, right? So in the end, we'll just remove a few vertices from each ai and take the union of all of them to be our dependent set. So in general, we'll let, okay, so delta I will just be the max degree of gi, and then in general, ai will be a gamma over delta I random subset of vertices of gi. And okay, in the end, we're just going to take the union of all the AIs to be our final independent set. So the point is that we need to show that all the AIs have a good size, like we have a good lower bound on their size, and we also have a good lower bound on how long we run this process for. Okay, and the main point, so the key lemma is that if you look at delta I, it's going to decay like exponential of minus gamma times I. But if you look at the vertices of gi, it's also going to, times delta. It's also going to decay in the same rate, exponential of minus gamma times I times the vertices of g. So if we look at if ai is it's a gamma over delta I random subset of the vertices of gi, we know its size will roughly be gamma delta I times the vertices of gi. Which now, since both of them are decaying the same rate, will just be v of g over delta times gamma, right? Okay, but then the other observation that is important is that, okay, so every AI has the same size, and how long we can do this for? We can do this as long as the delta I is large, right? Like as long as we haven't like fully destroyed our degree. So this holds when, so run until I is like 1 minus epsilon times log delta over gamma, right? Because then when you get to this point, then the delta will be very small. And if we run for this many steps, so the sum of the sizes of the AIs will be roughly 1 minus epsilon times log delta over gamma times gamma v of g over delta. So we'll have roughly what we want. Will be basically log delta over delta times v of g. So the main thing you need to show for this to hold is that these two conditions hold. And notice that until here, I haven't said anything about our co-degree condition, right? Like it didn't come in at all. So it has to come in when we are showing that these two conditions here hold. And specifically, it comes in when we're trying to show that the max degree is decaying like this. Because it is not true that max degree decays like this if you don't have like a co-degree condition. If you like don't have any type of condition in your graph, it's not true this decay behaves like this. Okay.
So maybe a small question here, if I may. So again, coming back to this problem of 2, like, can you imagine where should it appear? How should it appear if Redl-Nibble doesn't give it to us, but random regular graphs give it to us? Like, what is the difference between, like, does it mean that we just cannot generate our independent set randomly, or
So there is here's a question. So basically, if I give you a random regular graph, there is like no algorithm that we know to find a large independent set in that graph. So the only way we know how to show these large independent sets exist is via second moment method. So if I give you any like pseudo random graph, I don't know how to generate a large independent set, even if one exists. So the problem is that this thing here we're doing is algorithm. Okay, is algorithm.
Okay.
And then we know that it can't work, but
okay, makes sense. Okay, that's interesting.
Maybe I'll say a bit how we do these two things. We get these two things to work, and we get these concentrations. And the point here is that the concentration for the vertices is just going to be second moment method, but the concentration for the max degree, we need some like stronger type of concentration, and basically there we use a martingale argument, and this is where the code degrees is going to come in. So basically, I want to show the following. So I have this lemma here, which is that if you have a graph, so imagine you have our GI, and imagine the code degree of GI is going to be bounded by some eta times the max degree of GI. I'll call it delta I, actually. Sorry. Yeah, this delta 2 is okay. It's just max code degree, and then it's bounded by the max degree of GI. Okay, and then the main lemma we show is that the probability. So for every v in your graph, the probability that its degree in GI is going to be bigger than in GI plus 1 is going to be bigger than exponential of minus gamma times its degree in GI plus some alpha times its degree in GI is going to be fairly small. So it's going to be like some exponential of minus squared over gamma eta. So the point is that if eta is very small, this probability here will be very small, right? Like, because it's exponentially minus 1 over eta. So this is why the eta can be like a polylog or something. And this exponential of minus gamma is like the appropriate decay. So if you're always decaying by exponential of minus gamma, we get the correct bound here. We get the exponential of minus gamma I. So this is the expected value. It's going to be exponential of minus gamma times the degree. And then we have like this possible error here of alpha. And so I should say probably that so the expectation of dg I plus 1 of the given GI, what is it going to be? It's going to be just exponential of minus gamma times dgi. And the reason for this is very simple. Well, it's going to be because the probability that some vertex u is in GI plus 1, given u is in GI, well, what is this? It's going to be equal to, well, we have your vertex u, and basically it's going to be in GI plus 1 if you don't choose any of its neighbors to be in AI, right? So if all these guys are not in AI, then we're happy. But we're just choosing them independently to be in AI, right? So the probability for each one to not be in AI is going to be 1 minus gamma over delta I. And we're going to raise this to the power, the degree and GI of U. Okay, here there's something tricky because I promised, I want to say this probability is going to be exponential of minus gamma, but in principle, there is no reason why the degree of U in GI should be equal to the max degree. In principle, it could be smaller. But okay, so we do something very just kind of use a trick here, which is if you add edges to your graph, you can only decrease the size of the independent set. And since we just want to find like a lower bound for the largest independent set, we can add edges to our graph and still everything like, and still if we find an independent set in this new graph, it's still going to be an independent set in our old graph. So it's not a problem to add edges. So just add edges to make our graph regular at all points and regular with this size, with delta degrees delta I. So we get here delta I. And then the probability will roughly be exponential of minus gamma. And then, okay, here, then you're just calculating the probability that each vertex in its neighborhood is going to be in the new graph. So it's going to be just exponential of minus gamma times the degree. There is like another way of doing this instead. Like you could also like just tweak the probabilities. Like you could also like delete vertices for no reason, basically. Like you could say, okay, I delete the U from G, like I delete U from GI if it has a neighbor in AI, but I can also delete it like for no reason independently. This also works. Like you could also do that. But the thing we do in the paper is just adding edges to the graph. To make it regular. Okay. So now we have like the expectation behaves nicely. So everything, the probability of everything being included is going to be this exponential minus gamma. And so the expectation is this exponential minus gamma times the degree. And then, okay, so here's where the code degree condition is going to come in when we do the martingale, when we prove the concentration for this. Let me just put a division here. So let me transport this lemma to the next page. So the idea to prove the concentration is the following. We have let's say we have our set U, and it's going to be the neighborhood of GI of our V. And then we want to show that we want to show concentration for U intersection V of GI plus 1, right? So what we will look at is, look at U, and look at this larger set, which is the neighborhood in GI of U. And now we go from the vertices here one by one and reveal whether they are in AI or not. And then this defines a martingale here, because every time a vertex is in AI, we delete its neighborhood in U we delete its neighborhood from U, right? And we just want to know what is the size of U when you're done with this process. And so you can define a very natural martingale, which is, okay, you order these guys, x1 up to xm, and our martingale will just be some zt, which is zt minus 1. So we just do plus, basically we do plus p times the degree of xt to U t if xt is not in AI. Oh, sorry, it's a bit squeezed. So if xt is not in AI, and we just do z t minus 1 minus 1 minus p times the degree if xt is in AI. And okay, and then we have this martingale, and basically we just want to apply this martingale concentration inequality called Friedman's inequality. And to apply that, we just need to bound the increments of the martingale squared. But they have to do with the sum of the degrees squared. So I just want to show you that to just give you like the heuristic for where the co-degree condition comes from. So basically, like we need to bound the sum of degree of xt to u squared, where t equals to 1 up to m. But notice that this is just, you have some x here, and you're just looking at the number of cherries. So I have xt, and you're looking at the number of cherries with the head outside of u and the two points in u. So there's another way to count these cherries, which is just you sum over u and w in u and look at the co-degree. And now here's where we apply the bound on the co-degrees, just to say, okay, we bound these co-degrees, and this gives a bound on the sum of the increments squared in this martingale. And this is where, so this ties back to showing, okay, you have concentration because of that. So you get like a bound here of basically eta times size of u squared times delta I. Sorry, this maybe I'll rearrange this.
Okay. Yeah, once you finish this, can you also come back to the martingale definition?
Yes, of course. Sorry, I'll transport it.
So here it's u. You mean degree co-degree of xt and the u, right?
Yes,
like
sorry.
number,
okay.
Or not u, even v. I think you called it, right? It's the co-degree of, like, it's the intersection of the neighborhood of xt and u, right? This is what you mean.
Yeah, sorry. Yes. So this quantity here is the number of neighbors here. And I get, sorry, ut, I should define it. Ut is just u minus the neighborhood of g of a intersection x1 up to xt minus 1. So basically, like, we're as we do the martingale, we review a point, and every time it's in AI, we're gonna remove this many guys from U, right? Like, we just remove all its neighbors from U, and then like UT is just the things that are left after T steps here of the martingale. And then every time you have something in, your martingale goes down by exactly this amount, and every time it's not in, it goes up by this amount. There's something crucial about this martingale, which is, so we only want like one-sided bounds here. Like, we only want like the probability it's bigger than this. And then it's crucial that we want one-sided concentration, because the increments going up are of this form here, so they are much smaller than the increments going down. Like, every time we go up up by much less than when we go down. So the concentration for the upper tail is much better than the concentration for the lower tail, and that's important for us.
Yeah.
And I think that's all I want to say about this proof, basically. So I guess I'm running out of time. So.
Yeah, great. Thanks a lot, Marcelo.
Thank you.
Yeah. So you basically gave the whole proof, like modulo some details in this lemma. I didn't expect that you'll hear all of that. That's really nice. So is there any hope here that we can still avoid solving this Ramsey theory question and somehow argue that the graph we get from this Poisson process is like, I don't know, like a random regular graph, and then you have this 2 for free or whatever.
Oh, that would be super interesting, yeah. But it would be like a very cool idea, because it seems like you have like some randomness that you can use. Like you can like use some randomness about like this Poisson point processes things. So maybe you can like get some out of some second moment type method. But I don't know how to do this. It seems like
because you use very limited information about this, right? About this graph. So it from any point, you don't use much the fact that it's randomly generated. Just
It's also very little geometric information, right? Like the only geometry we use is this intersection of balls bound.
Yeah. But. Yeah. Oh, this is great. This is great. So, anybody has questions? Maxim?
Yeah, do you know any meaningful properties that hold one random graph and doesn't hold for another? So you have a random regular graph and you have this random graph from the Poisson point process that are essentially different.
So, for instance, this graph here has much larger cliques than a random graph because of the, like, if you have like a bunch of points close together, they form a clique.
Expansion properties for sure, right? I mean, if you think of D as being fixed and making L tend to infinity, then well, the diameter would be huge for. I think. I mean, it'll grow like. It wouldn't be logarithmic of the number of vertices or whatever, right?
Right, but yeah, but in a way, it's also like I think there is like some hope that in high dimensions these graphs do look like they don't look exactly like a random graph, but like they look enough like a random graph in high dimensions. There's some hope of that, and I guess this is what this Parisian-Zamponi conjecture is about. So the physicists have like some various conjectures of what the correct number should be, and one of the conjectures is this Parisian-Zamponi one, like that it should be exactly that, and that holds exactly if there is no weird structure going on in your graph. Like basically, the best thing to do is like it looks like a random graph, so you just do that. But it's hotly contested.
But what about the upper bound? So is there any meaningful upper bound, like any semi proved upper bound for amorphous arrangements or whatever? We have this Kabatansky-Levenstein, but it doesn't use any. It doesn't specifically use any lattice or anything. So nothing along these lines, right?
Yeah, I don't think there is. Yeah, the upper bound is very mysterious. I think like there has been almost no movement in the upper bound for the last 40 years or 50 years.
Mm-hmm. Yeah, that's cool. Thanks a lot, Marcelo. Any other questions? If not, then well, we can upload. Yeah. So if not, then we can finish the seminar. So thanks again, and hope to see you in person maybe sometime soon.